All right, so we're going to try and cover a lot of stuff in a very short amount of time. What I want to do is, I've only got 10 problems in this PowerPoint, but my basic concept or my basic idea tonight is to try and expose you to as much material as possible, but at the same time, calming if you're nervous about this section of the test, maybe calming it a little bit, because ultimately my big message about the FE is you don't get asked hard questions, you just get asked a lot of them. So some of this stuff, it might seem bad, but when you start tacking it and chipping away at it, you go, this isn't so bad at all. So I've got a few statics problems here at the beginning. I think we're just going to delve right into it. And I think this, I picked this problem because it's a pretty typical problem on the FE, and this is a nice get your feet wet kind of problem. Now, one of the things you'll probably notice is everything is in metric. When you get to this section of the test, it's very possible that everything is in metric. One thing I will say when you're on this, this portion of the test, if you're ever in doubt about your units, my advice is to convert everything back to like the standard base. Like if you've got kilonewtons or meganewtons or giganewtons or whatever, convert everything back to newtons. Convert everything back to meters, or kilograms or what have you. The idea is if you get everything into standard base and you do all your math right, you can back convert it later. I can't tell you how many times I remember when I was taking the test, it's almost like I spent more time on questions like this doing the unit conversions than I did actually doing the problems. So it's sort of a tip and trick that I recommend, especially for civil engineers because we don't deal with metric very much. So that's sort of my advice. Fortunately for this problem, it's not going to be that big of a deal. So the idea behind this problem is you've got a pretty complicated rope system, or pulley system, at least as it looks. It's really not that bad. But the idea is if I've got some 1,200 Newton lock, how much do I have to apply on this rope? How much tension must I apply in order to lift that weight, that 1,200 Newton weight? So this is nothing more than a static equilibrium problem. So we'll walk through it, and I think you'll see, oh, this isn't so bad. So maybe I can do this on the slide. I hope this works. This doesn't like that. That is a big image. Scale that down a little bit. Okay, so here's our image, and let's see what we can do. So problem one. Okay, so what I'm going to do is I'm going to take each pulley one at a time, and I'm going to see if I can determine the force inside this system. Now I'm going to start off with where my hand would be if I was on this system. The concept, or the idea is I'm going to pull on this rope. So let's see if we can look at pulley number A. All right, so pulley number A looks like this. I have, my little wheel or whatever on the pulley, and I have a rope going, like that, right? Okay, so I'm pulling on this with some tensile force T, right? Now, think about this. If I give you one end of a rope, and I'm holding a rope, and I pull it with, let's say, 20 pounds, you've got to resist it with 20 pounds, right? So that means that this force, just by that very nature, has to also be T, right? So equilibrium, what's that force? You tell me. If I got T going up and T going up, what do I have to have going down? There we go. Not too bad, right? Now we'll go to B. So B, same deal. Although follow it out, okay? So B going like that, right? So really what I've got is I've got this rope going like so. What's the tension in that rope for B? 2T. So what's going down? There we go. Oh. Not too bad, right? All right, let's do C. What's the tension in C going to be, that rope? 4T. So this is 8T. And if we look at D, now you tell me, here's the wheel. The rope that is going around D, what's the tension in that rope? Well, no, think about it. This rope here, this is the 8T. See, watch this. Let me put a little bit of color on my image. There you go. Because see, this is the first rope that we looked at, right? This is the second rope that we looked at. The third rope that we looked at, oh wait, I got that backwards. That's the second rope. The third rope does something about like that, right? So if I look at D, D looks like this and like that. This is 4T and 4T, right? This going up is 8T, right? So if I look at my block, all right, here's my block, right? 1,200 newtons, right? So what ropes are attached to that block? Well, I've got over here, I'm going to have a green rope holding that up, and I'm going to have a rope over here holding that up. So on the left, what's the tension over here? 4T. What about on the right? What is it? There we go. So if equilibrium tells me that everything going up has to equal everything going down, what's T? Answer's A. See what I mean? It's really not that bad, you know? But this is statics in a nutshell, isn't it? You know, sum of forces in a given direction must equal 0. Not too shabby, right? But yeah, I understand. But the big thing is to not overcomplicate the situation. Remember, secret weapon of structural engineering is a samurai sword, and all I'm I'm looking at these individual ropes, but really all I'm doing is looking at a given wheel and cutting a section. That's really all I'm doing, you know. All right, give me one moment. I'm gonna have to. Oh, not that. I'm gonna have to fix my presets. Because that line weight is just too much. Let's see. That's a little better. All right. Okay. So Now let's add a little bit of dimension to this. So now we've got a little bit more going on. We've got the X direction and we've got the Y direction. We've added some scale to this. So let's sort of let's take this step by step. Okay. So we have a sign that's got a mass of 150 kilograms. That's actually kind of a heavy sign. The sign is attached to a wall by a pin right here and a cable right here. Okay. So what I want to know is what's the tension in the cable. Now, this is a statics problem. Okay. So I've sort of subtly included something that might trip you up on the exam. Okay. Help me out. The equations of equilibrium are that the sum of moments must equal 0 and the sum of what must equal 0? Sum of moments and sum of forces. I didn't give you a force of that sign, a weight of that sign. I give you a mass of that sign. So I must take that sign's mass and adjust it by gravity to get a weight. See what I mean? So, right, I mean, that's something really easy that could trip you up. Now, the choices are kind of nice, but like if I let's say I gave you these choices and one of them was 10 times more than the other, you might actually pick the smaller one because you didn't adjust it by gravity. So, something to think about. All right. That is big. All right. Okay. So before we do anything, let me compute the weight of this sign. So it's the mass times the gravity. So one big thing to remember is that if I take kilograms and multiply it by gravity, meters per second squared, kilograms times meters per second squared, that gives me newtons. And what is that? (1,471.5 newtons). Okay. Now, while this doesn't look much like it, you can kind of treat this problem a lot like a truss analysis. Now, what I mean by that is this. All right, let's look at a free body. All right, so here's my sign, as Bill Engvall would say. You like that? Here's your sign. Now, I have a force going down of, as you say, 1471.5 newtons, right? Okay? Now, I have a hinge at, we're calling it B, right? Or a pin at B. What must be true about what's going on at B? Anytime you see a pin or a hinge, what does that tell you? The sum of what must be 0 there? Sum of moments, right? See, I can take this door and I can freely rotate about the hinge. I can't, take the door and yank on it, but I can rotate easily. See what I mean? Same thing here, okay? So, the same thing is true at A or B. Sum of moments has to equal 0, okay? So that's got to be true there. All right. Now, I've got this point C right here, and I have a cable. Now, that cable is going to be subjected to some level of tension, right? So tension means yanking on it, pulling away. So we'll say the tension in that cable looks something about like this. Now, you ask me, What I love to do is split things up into x and y. So this is tx and ty, okay? Now those components are related, right? Now, one of the big secrets behind how to do statics problems really easily is what's called the principle of transmissibility. And I know that's a really, really big word, but it's a big word for a really simple concept. Let's say you and I are holding a rope, okay? And we're pulling 20 pounds, right? So you're pulling 20 pounds and I'm pulling 20 pounds, right? We're sitting still, tug of war, right? Neglecting how much the rope sags, does it really matter if you and I are here or if I'm all the way over here? We're still pulling 20 pounds. So this force can, and where I locate this force can go all the way up and down that line. I can say that Tx and Ty is here. I can say Tx and Ty is here. I can do anything I want, okay? What I'm going to do is I'm going to put that Tx and Ty, I'm going to put it right there. Let me erase that. And the reason why I'm doing that is because if I sum moments, moment is a force times a distance, this part's going right through there, so I don't have to consider it. That make sense? Okay, all right. All right. By the way, what is this distance from here to here? Did they give us that? 2 meters. All right. Now, if you haven't seen this before, this is kind of how I like to sum moments. What I do is I say the sum of moments about B has to equal 0, and then I draw myself a little table. And I say that everything spinning that way has to equal everything spinning this way. So, I look at point B, and I say, all right, at point B, I have 1471.5. I've got this weight acting at a distance of 2 meters, right? And it's going like this, right? So, say, that goes over here. And then I've got Tx and Ty. Tx doesn't cause any moment at all because it's going right through B. Ty does, and what's its moment arm? 2 meters. So, oh. So, 1471.5 times 2 has to equal Ty times 2. What's Ty? 1471.5, right? Pretty simple. The rest is trig. Watch this. The rest is trig. So I'm going to draw a triangle. And this is a right triangle. Now I'm going to say that Tx equals some value. I don't know what that is. We know what Ty is. But what we're really after is the tension in that cable. How do we get that? We do a little bit of trig. Help me out. What is this dimension? What is this dimension? So how do we find what that dimension is? Oh, I can do a little better than that. How do we find out what that is? Pythagorean theorem. So what I'll say is the hypotenuse is what's that? Huh? 2.5 even? All right. Everything else is just a slope ratio. Watch this. Ty is to 1.5 as this tension is to 2.5. That's it. So, therefore, or 2.5, sorry. And what's that? Right? And that'd be all she wrote. Is that me? That was me. Isn't too bad, right? Simple stuff, right? Honestly, the static stuff that you get is really stuff like this. You might get the occasional centroid or something, but that's about it. I got one more statics problem just to get the, you know, the mechanics juices flowing, if you will. All right. So here I've given you a simply supported beam, and this is about as far as I'm willing to delve into the realm of structural analysis, because I go any further doing things like shear diagrams and moment diagrams, and now I'm just back into what I did in the first video. So I don't really want to repeat things, but I do want to at least go through a little bit of basic statics just so we're all clear. Okay, so what's the reaction at point C? So a strategy, let's talk about strategy. If I want to determine the reaction at point C without doing any math, what do you think I should do first? Like what would your strategy be for this problem? So saying what you should do first, just what would you do? But okay, what do you mean work down the beam? Doing what? At summing moments where? There you go. Some moments at A, because think about it in terms of unknowns. You got two unknowns here, one unknown there, just some moments here to determine that reaction. Make sense? All right. My goodness. All right. So let me actually make this a little bigger. All right. Okay. So we've agreed that we're going to sum moments right here. Okay. So I'm going to do the same thing I did before. Sum moments at A equals 0. Draw myself a little table saying everything going this way has to equal everything going this way. Okay? Now before I do that though, I want to indicate a couple things. Okay? Number one, this is a hinge over here on the left. It's A, so that means I have a vertical reaction and a horizontal reaction, right? So we'll call this AX or AY and AX. Okay? Now, this one here has a vertical reaction as well. We'll call that CY. That's what we're after, right? Now, when you do these types of problems, the first thing you have to do is make a guess. So I'll just say, what the heck, let's guess it acts upward. You know, guess this one acts upward. Maybe guess this. Whatever. If you do all of your math and you get a negative answer, does that mean it's time to curl up in a ball and give up on life? No, all it means is that you made the wrong guess. You guessed upwards, and if you get a negative answer, that means, whoop, it's actually going down. Does that make sense? All right. So we'll sum moments at A. So what we do is we just take each force one at a time. Okay? So if I'm summing moments at A, does AX cause any contribution? No, it's going right through it. So that's done. What about AY? What's that? So nothing there, right? Let's deal with the simple one. What about the 2000? Does that cause a moment? The one on the very right? Yeah. Okay. So should it go on the left side of the table or the right side of the table? Right side. So we put 2,000 newtons acting at a moment arm of what? 1 plus 0.6 plus 0.8, so that's 1.4, 2.4, so 3, right? Make sense? All right. So that takes care of that one, right? Now, the 1200, that is a concentrated moment acting in the clockwise direction. So you just straight put that number right there. Simple. Now this next one, distributed load, 10,000 newtons per meter acting over a distance of 1 meter. So what we've got to do, if you remember, we collapse that into a single point load. 10,000 newtons per meter acting over a distance of 1 meter, that's 10,000 newtons. Now, how far is that from here to here? Half a meter, 0.5. So, on this side, make sense? All right. So on the right, we have 6,000. On the left, we've got, what do we have? We have 1,200 plus 5,000. That's 6,200. What are we missing? Did we get every force? There we go. That's what we're missing. So this is 6,200. So cross that. We've also got CY. And what's that moment arm? 2.4. So this is plus CY 2.4. And see, that's why I like to take the free body diagram and just say, all right, let's just start crossing them out and make sure we took care of everything. You know what I mean? It's one of those things, if you're on the exam, wait, something doesn't make sense. 6,200 doesn't equal 6,000. Math, you know? Stuff like that happens on the exam. It's okay. So solve this equation. You get 200 Newton meters equals CY times 2.4. What's CY? Say it again. Is it positive? So that means it is acting upwards. All right. Sound good? Not too bad, right? Simple stuff. Okay. Now let's get into the fun world. Let's get into some dynamics. So you got a mass matrix and a stiffness matrix. Kidding. She got it. Now, one of the things you're going to find with a lot of these dynamics problems is that they're strikingly like probably what you did in physics. That can happen on the exam, and a lot of this stuff is pretty similar. So you're like, oh, okay. All right, so the little tray came off on the outlet. That'll be all right. All right, so so we've got a particle. It's starting from a rest. It experiences an acceleration of 3 meters per second squared for 2 seconds. All right, and after that 2 seconds, it returns to rest and in an additional distance of 8 meters. So assuming all the accelerations were uniform, what was the total time elapsed? All right. Excuse me. Okay, so let's sort of take away a couple things. Okay, all right. Number one, it seems to be that there's 2 events happening with this particle. The first event is that it starts off with, it starts from rest and it experiences an acceleration for 2 seconds, right? And then the next event is that now that it's moving, it goes back to rest over in a distance of 8 meters. Does that make sense? Okay. So, so 2 events. Three meters per second squared for 2 seconds. Then B, return to rest after 8 meters. Now I'm going to break out some equations that you can find in your FE reference manual, but also this is stuff I'm almost positive you've seen before. And you'll see this and go, oh, okay, I remember this. So let's look at situation A. Okay, so we've got an initial velocity of 0 meters per second, right? It starts out at rest, right? We have a change in time of 2 seconds, and we have an acceleration of 3 meters per second squared. Remember this? VF equals VI plus A delta T. Y'all remember that from physics? Yeah. All right. So this is 0 meters per second plus 3 meters per second squared times 2 seconds. This is VF is 6 meters per second. So here's what's going on. Okay, so I'm the particle, right? I'm standing still, right? There's 2 events going on. The first event is that I accelerate for 2 seconds. So what does it mean to accelerate? It means to go faster and faster. So this is what happens for 2 seconds. I start off at rest and I go like this. And I start to get faster and faster. Then after 2 seconds, I'm moving at a given speed. What speed am I, or what velocity am I moving at? 6 meters per second. Sound good? So at the beginning of B, that's the big thing to keep in mind. At the beginning of B, my initial velocity is what I ended up with on the first step, 6 meters per second squared. Make sense? Or meters per second, I'm sorry, meters per second. Okay. Now, what does event B state? I return to rest after a distance of 8 meters. So my final velocity is going to be standing still. Excuse me. What about my change in distance? 8 meters. Make sense? All right. Now, here's another equation. I know you've seen it before. Oh, I can do better than that. There we go. I know you've seen this before. Remember that? It's been a while, I know. But I know you've seen that before. What don't I know in this expression? I don't know the acceleration, right? Because think about what's going on. So the particle got faster and faster and faster, right? And then once it was going at that speed, it slowed down. Now we know it slowed down over a distance of 8 meters, but we don't know at what rate it slowed down. And that's what we're trying to determine right here. Make sense? All right. So if I solve for A, what do I have? I have VF squared minus VI squared over 2 delta X. So, excuse me, 0 meters per second squared minus 6 meters per second squared over 2 times 8 meters. So negative 6 times 6, that's negative 36. Negative 36 over 16, that comes out to be about negative 2.25. Now, we're calculating a negative acceleration, okay? Negative. Does that make sense? Well, yeah, it makes sense because the particle is slowing down. It's slowing down, okay? Now, so that makes sense, right? Now, here's the issue, though. What we're after is the time, right? We want to know how long it took the particle from the beginning to speed up and then slow back down, right? So, how do I calculate the time? Well, acceleration itself is a change in velocity over a change in time, right? Change in velocity is the final velocity minus the initial velocity, right? So if I want to solve for the change in time, it's VF minus VI over A, right? So, where is this? All right, so 0 meters per second minus 6 meters per second over negative 2.25 meters per second squared. What does that give us? Huh? 2 2/3, so 2.67 seconds. Does that make sense? Now, is that the answer? Huh? There you go. That's what I wanted to get at. It took, the particle had to speed up and then slow back down. So what is the answer? It's not 2.67, it's 4.67. Make sense? I mean, honestly, I broke out some equations you haven't seen before, or haven't seen in a while, but I know you've seen them before. That's what I meant to say. Not too bad, right? So, just for posterity, I'll say T total is T from time A, from T from B. And then that's C, right? There we go. Okay. Sound good? Okay. Now this next one, I'll say this. if this problem here, if it left you feeling, well, gosh, I don't remember these formulas, the next one will help you remember where they came from. The next one does involve a little bit of the C word, a little bit of calculus, but I actually think it's about the easiest calculus that you could do. Okay? Now, let me explain why. Anytime that you see an e to the t on the exam, be very, very happy. Okay? What's the derivative of e to the x? What's the integral of e to the x? E to the x, right? Anytime you see that, that's usually a blessing in disguise. You see what I mean? For that very reason. All right. A 50 kilogram mass initially at rest is acted upon by a force. The force varies as a function of time. You know what I mean? So the idea is, you know, I've got this mass, right? And instead of just applying a constant force, what if I lean into it a little bit? So the force varies as a function of time. So how much does it displace after 4 seconds? This is a perfect review of the equations of motion. Okay? Now, let me get this. Okay. Okay, so to start off, we have a 50 kilogram mass being acted on by a force. Okay? Now, if I've got a mass and I've got a force, what should I be able to solve for? Force equals mass times gravity or acceleration. So if force equals mass times acceleration, and for the purposes of the problem, I'm going to leave the units off. The reason why I'm going to leave the units off is if I say kilograms and keep all my velocities in meters per second squared, that gives me newtons. So as long as I keep that understanding and keep everything consistent, everything will be good. All right, my force is 50 e to the t, or e to the 4, e to the t. What's my mass? 550 times a. What can I solve for? I can solve for a, right? Therefore, a is e to the t divided by 11. Does that make sense? Sound good? Okay, now, help me out. X is position, V is velocity, and A is acceleration. Can't spell tonight. Help me out with a couple things. If I take the derivative of position with respect to time, what is that? Velocity. If I take the derivative of velocity with respect to time, what do I get? Acceleration. But that's also the second derivative of position, right? Make sense? Now, what we're doing in this problem, however, is we're working backwards. We've been given A, right? So if I've got A, I'll do this over here on the left just because I want to keep this concise. If I have A is the derivative of velocity with respect to time, how do I determine what the velocity is? Well, would you agree that A dt is dv? So how do I determine what v is? I integrate. Make sense? Okay, so here's my acceleration function. I propose that to get the velocity, I integrate the acceleration. Make sense? Now, what is the integral of e to the t? E to the t, right? Now, if I have a function times a constant, I can factor that out, right? So if I have the integral of 2e to the t, it's 2e to the t. If I have the integral of 7e to the t, it's 7e to the t. 1 over 11, it's just 1 over 11. Now, is that the answer? Well, there we go, plus c. I'm going to call it C1 because we're going to have another one here in a second, although it doesn't matter. We're going to be able to solve for that constant pretty easily. So, I've got that the velocity is e to the t over 11 plus c1. I got that damn c1 there. How do I get rid of that? I get rid of that by using boundary conditions. Okay? How did this particle start out? At rest. It wasn't doing a thing, right? So if it started out at rest, what is its initial velocity? 0. So at t equals 0, the velocity is 0. So let's write that out. At t equals 0, v equals 0. So v at 0 is e to the 0 over 11 plus c1. That equals 0 on the left. What is anything raised to the 0? 1. So 1 over 11 plus c1. What is c1? Minus 1 over 11, right? So another way of writing velocity is e to the t over 11 minus 1 over 11. Not too bad, right? Bringing it back, right? And honestly, this is, if you're having a hard time remembering formulas, I think this is actually an easier problem. All right. Sound good? So now we have a nice plug and chug expression for the velocity. Is that very useful for us for this problem? Now, the problem wants the position. So that means we got to take this whole process and do it again. So for position, x equals the integral of e to the t. Whoa, what am I doing for? Keep getting ahead of myself. We have to integrate that, right? So the integral of e to the t over 11, that's e to the t over 11. What about this? What's the integral of a constant? Constant times t, right? So we have e to the t over 11 minus t over 11 plus c2. Call it c2. Particles initially at rest, so its initial displacement is 0, or its initial position is 0. So we'll say x at 0 is e to the 0 over 11 minus 0 over 11 plus c2, and that whole thing has to be 0. That tells us that c2 is also minus 1 over 11, and we get x equals e to the t over 11 minus t over 11 minus 1 over 11. What do we do from here? Plug in 4 seconds. So therefore x at 4 seconds is e to the 4 over 11 minus 4 over 11 minus 1 over 11, and that equals what? And going back to the problem. This isn't too bad, is it? Just bringing it back, you know. And mostly, here's the thing. Most of this stuff that you see on the exam is fairly basic. I mean, this was an involved problem, but it didn't involve crazy theories that you haven't heard before. You know, that's what this test is after. There we go. So, all right. Next one. Okay. Now, let's test y'all's memory banks. Okay. So a 2-kilogram ball of clay, is this a soils problem? Net negative electric charge has a cohesion value, right? A 2-kilogram ball of clay moving at 40 meters per second collides with a 5-kilogram ball of clay moving directly towards the first ball with velocity of 10 meters per second. What is the final velocity if both of the balls stick together after the collision? So, you all have had these types of problems before. I want to see if you all remember this. If you have a mass and a mass, and right, what law does that bring up in your head? The law of conservation of what? Momentum. The law of conservation of momentum. Remember how you calculate momentum. Momentum, not momentum. Momentum. Mass times velocity, right? Mass times velocity of the first situation has to equal mass times velocity of the final situation. Remember that? That's all this is, okay? So, law of conservation of momentum. Okay? So, all right. Let's see if we remember this. Okay. Now, we've got a ball of clay. I'll call this ball of clay 1, and we've got ball of clay 2, right? They're both headed towards one another, right? Both head towards one another. Yeah, like Power Man 5000 song, When Worlds Collide. I remember things, okay? So let's look at the first ball. Its mass is 2 kilograms, and its velocity is 40 meters per second. Now, for the second ball, its mass is 5 kilograms. Now, what's its velocity? There you go. Now, excuse me. So, let's figure out the momentum going into this collision. Okay, what's the momentum going into this collision? So, sum of m, v, and I'll say initially, at the very beginning. So, at the very beginning of this, you've got ball 1 going like this, ball 2 going like this. So, what do we got? We've got 2 kilograms, 40 meters per second. I have squared. That is not right. So that is what? 80, negative 50, 30. So So which ball has more momentum? It's ball number 1, right? Make sense? So the momentum going into this situation has to equal the momentum coming out, okay? So here's my initial momentum, all right? My final momentum is the final mass times the final velocity. What is the final mass? 7. Because they stick together, right? So therefore, what is 30 over 7? Not too bad, right? Any questions? Are you feeling a little better about this stuff? Feeling a lot better. Okay, all right. Okay, I've got one more dynamics question, and this one honestly is going to test your memory more than anything, but honestly this is also a function of just going through the FE reference manuals. From what I understand, Dr. Chen does, like, he actually gives you the handouts from the FE reference manuals, so that's actually a really good thing so that you all have seen that stuff before. Okay, so problem number 7 deals with some, centripetal acceleration, essentially, or centrifugal. I can never say those two words appropriately. I get tongue twisted. Okay, so we have a child with a toy airplane. They're sort of going like that with it. It's a 1 kilogram toy plane, and it's flying horizontally in a circle. Actually, it's going like that, with a string where the string is 1.5 meters long. And the string is always in the plane. That's just to say we're dealing with a circular flight path. If the plane flies at 10 meters per second, what's the tension in the string? This is actually a pretty straightforward problem if you know the equations going into it, which this is where I wish I had printed off the FE reference manuals. I couldn't really have time today, so I'll send you all the links. Do you all have the PDF of the reference manual? Okay, all right. Excuse me. So I'll do my best to draw this out. So here's the center. There's the flight path, right? Here's the plane. That's about the best you're going to get from me. Now, this radius is what? 1.5 meters? Okay. This has a mass of 1 kilogram, and it's moving at a velocity of 10 meters per second. I guess I should do. Oh, goodness. R is 1.5 meters. So this is all about centripetal acceleration. It's AC is V squared over R, which is 10 meters per second squared over 1.5 meters, which comes out to be 66.67 meters per second squared. And then lastly, since we're trying to determine, what's going on inside this cable is holding it taut, right? We need to determine the force in that cable. Well, if we know the mass, and we know the acceleration. See where I'm going with this. This might have actually worked out for the best that you don't have the manual with you today, because if you do have the PDF copy, maybe I challenge you to find that formula. Now you actually have to go and look it up. Oh, good. You have to study? Oh, God. Oh, no. Woe is me. All right. Is that all right? Okay, all right. I have one final topic for you tonight and 3 questions. Topic very near and dear to my heart, mechanics of deformable bodies, or strength of materials, or mechanics of materials, whatever you want to call it. It's all the same stuff. What I tried to do was pick out 3 problems that I think comprise a grand cross-section of that class without doing too much related to beams, because we do that, so much of that in structural analysis that I don't want to repeat material. So what I've got is an axial problem, a torsion problem, and then a shear stress problem. And I'm going to just sort of test your concepts and remembrances of mechanics of materials, but I can talk about this stuff all night. So I have a bar. It is the bar is got a 10 kilogram axial load. It's uniformly carried by an aluminum pipe. The outside diameter is 10 centimeters. The inside diameter is 9.6 centimeters. Now the pipe is 1.2 meters long, got Young's modulus. If I've got that axial load on it, how much is the pipe compressed? And I've got these different dimensions. Now, the decimals that I'm about to show you are going to get a little nasty. The reason why is, when in doubt, get everything into newtons and get everything into meters. Okay? Make sense? All right, let's see how this works. Now, don't get me wrong. There are better ways to go about this, but I think that if you're not used to using metric, this is the most sure way to get the right answer. So, all right. Will this let me write? Will this be nice? Maybe I'll just... What's that? That is a very smart observation. Well, I'll be in college. Gee. Extra credit. Okay. Now, to bring back a little bit of dynamics and all that physics stuff, it's a 10 kilogram axial load. That's a trick part to it, isn't it? Can't have a load in kilograms, right? The load is in newtons, right? So P is 10 kilograms times 9.81 meters per second squared, which is 98.1 newtons. In this section of the test, that's actually a nasty trick, but yeah. All right. How long is the pipe? 1.2 meters. Now, Young's modulus, or E, is 75,000 megapascal. Now, let's test your memory. What is a pascal? Newton per meter squared. So this is, help me out, 75,000 times 10 to the 6 Newton per meter squared. Would that be a fair statement? So now everything's in consistent units. Now, let's look at this pipe, okay? So the pipe, maybe I'll draw it up here. Here's the pipe. And we're after the area of this pipe. and I'll explain why. But first off, let's see if we can compute it. Now the outside diameter is what? 10 centimeters or point what? 0.1 meters? Or 0.01? 0.01, yeah. Right, no, that's 0.1. Yeah, because 10 centimeters, yeah. 0.1, right? And what's this inside diameter? It's 0.096. Right? Okay. Now, this number's going to get a little hairy, but bear with me. Okay, so how do you calculate the area of a circle? Just in general, how do you calculate the area of a circle? Pi d squared over 4. So for that red shaded region, the actual area of the pipe, I need the pi d squared of the outside minus the pi d squared of the inside. So really what I need to do is A is pi times the outside diameter squared minus the inside diameter squared over 4, right? Now, you all have Casios. Tell me what you get. It'll be a really small number. That's okay. You can tell it to me in scientific notation if you want. What's that? No, because what you're, here's, if you wanted to do it that way, what you would have to do is this. You would say the circle, the circumference of that circle times the thickness. So your way, you would say pi times 0.098, I don't know why that's coming out so choppy, times 0.04. Yeah, that would be doing it your way. Where's the 0.98 coming from? Because that's how thick it is. Or no, 0.02, 0.02. Right, because that's how, huh? That's the thickness. That's how, because see, look. Or, no. Well, hold on. Maybe see, it's my decimals. I'm getting it mixed up too. How far is it from there to there? It'd be 0.0. No, 0.002 because there's one here. See what I mean? So I forgot a 0. Say it again. Now, does that give you the same answer as well? The one up top? It should. Yeah, because this part right here is the circumference. Hold on, let me do this. So this part, remember that's how you calculate the circumference of a circle? If you took a string and stretched it around the circle, that's, the circumference of that middle segment throughout the center of the circle. And if I took that length and multiplied it by that thickness, I could get the area that way. Now, why did I calculate? I've got a P, an L, an E, and an A. Let's see if you all remember this. If I have a bar, which is essentially what I've got an axial bar, and I'm taking it and I'm either yanking on it or squishing it. How do I compute the deflection? How much it shrinks? Remember that? If you forget the equation, it's okay. Watch this. Do you remember this equation? I mean, please, you remember. I hope you remember that one. The stress and strain relationship, right? Now, how do we calculate stress? Load over area, right? Equals E times, what is strain? It is the change in length over the original length, right? Remember, it's sort of the percent of how much you elongate, right? So I can say that this is the change in length over the original length. And what am I after? I'm after how much the length changed. So plug and chug, and I get, or rearrange, and I get delta equals PL over EA. So look at what I've done. Now, I know the numbers are kind of messy because it's metric, but look what I've got. Newtons, meters, Newton per meter squared, meters squared. If I calculate this change in distance, what should it come out to be? Meters, right? So I'll do this here on the bottom because I'm running out of room. So I'll do better than that. All right, so P is 98.1 newtons, 1.2 meters, 75,000 times 10 to the 6 Newton per meter squared, 6.16 times 10 to the negative 4 meters squared. What does that come out to be? All right, so 2.5. Now, what's the units? What's this? Do you have, how many zeros do you have here? Let me see your calculator.
Well, I divided by the answer, so now it's going to be.
Oh.
I'll check.
It is -6. I know that. Okay. Now, what are the units? Meters. Now, how do I get that in millimeters? Well, remember, millimeters brings your decimals back. So that'd be 2.5 times 10 to the negative 3 millimeters, right? Because think about it like this. Throwing that milli on there, it's more millimeters, right? Make sense? So how do I express 2.5 times 10 to the negative 3 as a number? It'd be 0.0025, right? You know, remember this? You know, 1, 2, 3. So what's your answer? This isn't too bad, right? It's been a while, I know, but it's not too bad, right? Well, in all honesty, I actually might have too, just because it must be late and my caffeine's wearing off, but I was having problems with decimals up there earlier too, so. Huffman though would have covered that one, right? With stress strain.
I mean, I've seen them all before. I wouldn't have thought right now to use it, but that's because I haven't started reviewing it that much.
One of the nice things, though, about the manual, I will say, if you recognize from the problem that it is a member that is being subjected to an axial load, being gone like this, the manual will literally have this formula in it, guaranteed. It's like on the first page of the mechanics of materials section, guaranteed. I mean, I promise you it is. The next problem that we're going to do is the same way. Okay, it's the same way. In fact, I'll issue the same challenge. I issue you challenge you to find this formula in the mechanics of materials section. The next problem involves two formulas that I also challenge you to find. All right? So, let me go to the next one. Oh. So, with this problem, we're doing something very, very similar. Instead of taking a bar and yanking on it, we're taking a bar and we're twisting it. Okay? Now, I'll show you a couple things here right off the bat. These are the formulas that I challenge you to find. Well, I guess I got three. All right. For a bar, remember this, PL over EA. All right. That's for if you take a bar and yank on it. If you take a bar and twist it, you know, like you're wringing out a sponge, its angle of twist is TL over GJ. I challenge you to find that formula in the manual. When I teach mechanics of deformable bodies, I teach axial members and then I teach torsion because they're so alike. Even though you're doing something completely different to the members, the mechanics are very, very similar. It's a given effect along the length of the member. Now, we've got a pipe that is subjected to a torque of 100,000 Newton meters. So that's our T. That's how much we're twisting it. The length of it is 3 meters. Okay. Now, the tough part is this G and this J. Now, let's start off with G. Okay? Let me say this. Okay, so let's talk about Young's modulus. Young's modulus is a characteristic value for a given material about its axial strain, like steel. Modulus of elasticity of steel is 29,000 KSI if we're dealing in US units. So if I take a member and I apply some stress, it deforms, right? The relationship between how much it deforms and how much stress I apply is Young's modulus, okay? Now Young's modulus is for pulling things this way. G is the shear modulus for if you shear it, okay? Now how do we calculate that? Okay, so I've got a few formulas I challenge you to find in the manual. That's one. Now for the shear modulus, E is 210 gigapascals. I'm not going to convert that right now. And nu, our Poisson's ratio, is 0.3. The second formula I challenge you to find is how do you compute G? And you compute that by taking E dividing by 2 times 1 plus nu, which we covered that in finite elements, didn't we? Did we do that? Or did I show you all that in finite elements? I can't remember if I did or not. All right, that's formula number 2. I challenge you to find this one. All right. So here, let me move that over here. So one of you compute G and tell me what it is. So 210 divided by 2 times 1.3. $80.77. Okay. So that's 80.77. What is going on with my pen? It's like cutting out on me. What the? What? Okay, it's out of ink. No, I'm not kidding. It's like, I'm getting a little, oh, I'm getting ticked off. I'm not kidding. It's like, all right. back to the board. Okay, so what the, hold on. I really think it's out of ink. I swear, I just wrote the number 9. I swear I did. Hold on. I'm not happy right now. Greg is getting upset. I'm just saying. Hold on. Let me try something. Let me close this. I'm going to put this on my V drive. We'll call this okay. And close all this. So let me just open up a blank one. Or maybe these 2 programs were way too much for this computer to handle. Is it unplugged or something? Well, I don't think you can unplug it. All right. Sorry, internets, but we're going to do the other problems on the board. So maybe I'll upload a video later. But that's all I got for the internet.